Good morning. I welcome you to IT 5437. Actually, it's the computer vision. So today we will start with the fundamentals of image processing and computer vision as a start. So I want to introduce this course to you. Uh, First, I will show you some things that people have done with computer vision. Then in the latter part of the course, I will get you started with basic image processing operations. So that's the plan for today. So I studied here at Morato University in the electronics department. And then I joined the Western University in Canada for my higher studies. That's where I started studying computer vision. Um, so this is a beautiful university during winter time. You can see one picture during winter time. Yeah, so the course outline. So first of all, we will look at today the basics of image processing and computer vision. Uh, so actually, it will be the introduction. So in the latter part, we will talk about the sampling, interpolation, so-called point operations, filtering, that's using the convolution operation, then edge detection, feature extraction, optic flows, and so on. Now, how to do these things? Actually, we will be writing small pieces of code uh, to understand this properly. The coding will be in Python, but I hope the coding will be so simple. Only the concept is important. You should be able to start coding in no time. Now, this is the very basics of image processing. Then afterwards, we will go into a slightly more high level image processing tasks called, or computer vision tasks called filtering and alignment. I will describe them later in the slides. So least squares fitting, voting methods, ransack transforms, image stitching. We will talk about those things. Then we will discuss how images are actually formed using cameras, how light goes through the camera and an image is formed, briefly about color also. Then we start the 3D vision part, where we think about how two cameras uh, uh, image one object that is seen by both the cameras. And we'll be able to make relationships between these two views. So this two-view geometry is called epipolar geometry. So we will study that part. And then that leads to so-called structure from motion, where you can use multiple views of a scene to make a 3D reconstruction. But these 3D reconstructions are just point sets. They are not dense reconstructions. It is possible to make a dense reconstruction using the new techniques that are available called neural radiance fields. We call them nerves. This was discovered in 2020, and then so-called 3D Gaussian splatting, which was discovered in 2023. So very new techniques. We will go through these techniques also. Then we will look at image segmentation. Segmentation is very important for medical image processing, for example. That means you have a tumor and you have to demarcate where that tumor is. So there are some simple techniques called thresholding, region growing, snakes, gap cuts. And then we will briefly introduce the deep learning based segmentation methods. And as a sixth topic, we will look at deep learning for vision. So basically, we will look at the image classifiers and the networks that can do image classification. Then object detection, we will look at briefly the classical methods, not too much. I think classical methods are not used now. And then we will look at the deep learning based methods, so-called two-stage detectors. The famous detectors called RCNN, fast RCNN and faster RCNN. And then the single stage detectors, the well-known YOLO and so on, how these things work. Then afterwards, we will look at some recent topics, so-called vision transformers, vision foundation models, so-called CLIP, it's a vision language model, segment anything models by Facebook, those vision language models, and briefly about generative models. Sorry about the spelling mistake. Yeah, this is the curriculum that I want to teach you in this course. I'm very excited about this because I'm 40 years old now, but for last starting from 2002, 2002, yes, I have been doing this computer vision field. It's okay. Yes. So now I will introduce this curriculum that I described you in slightly more detail. So if you have any question, don't hesitate to ask questions. You can type in the chat. Some of you are already typing in the chat. That's very good. Or you can just turn on the mic and ask. Absolutely, there's no problem with that. That's why we do it in this fashion, right? Otherwise, I can record these lectures very fast and let you watch them. So because you want to ask a question only, we have this mode of everyone joining the meeting and discussing. So therefore, don't hesitate to ask questions. Um, yeah, so this is quite exciting. So I will show you why this is exciting later on in the slides. Yeah. So first one in under image processing and early vision, which we are starting today, we first of all look at the sampling and interpolation. Now you can see this image is a little bit coarse. You can see the dots and so on, but you can increase the resolution using some method. Then the image looks slightly smoother. So this is done by interpolation. So some interpolation is not extremely good, but there are the deep learning methods also of increasing the image resolution, but we will look at some interpolation techniques. And then some little bit of Fourier analysis of to see the frequency content of the image. Then we will look at the so-called linear filtering. This is a very important operation. As you know, the convolution neural networks are based on this linear operator. What that means is you have an image. I think this is skin of a giraffe or something. And then you have some image looking, we call it a kernel. Actually, this is a so-called derivative kernel. It finds the um, um, large changes in intensity. So you can see when there's a large change in intensity, for example, here there's a large change in intensity from white to black. Yeah, those regions will be emphasized due to this filter. So this is called linear filtering, and we will understand how to design some of these kernels. So we call them kernels. Yes. So if you take the convolutional neural networks, the deep learning technique, these kernels are automatically discovered in those methods. Okay. Then we will look at the so-called feature extraction. This is very important. If you want to navigate a robot or something through this corridor, it will detect these corners. And based on these corners, it will be able to find out where the robot is with respect to the environment. So then you can navigate the robot. So these are called feature extractors, how you detect corner-like structures. But then you describe them using a so-called a signature also. So you can see there are other corner-like structures. They have described this is called blob detection. We will understand how to do these things by ourselves. Then the final topic in this is optic flows. Optic flows is if you take 2 frames in a video, how the pixels have moved. So you can see these, because the cyclist is going this way, these little dots are moving this way. That's why you can see small arrows in blue. But these 2 people are moving that way. So therefore, so are the arrows. Okay. Yeah, that's about the early vision or image processing parts. Then we will look at fitting and alignment. Now assume that you have these edges. We use some technique to discover these edges. Now using for these edges, can we fit some kind of a line to these edges? You can see these lines have been fitted to these edges, the red lines. So this is an alignment. We will understand how to do these kinds of alignments. Another form of alignment is assume that you have a rectangular board or something, a billboard or something. Can you display an artificial advertisement on that? This is also once again alignment. You can see, although the advertisement is rectangular, it has been warped to look like a trapezium, right? In this case. So how can you do these kind of things? So this is called alignment, and one application is image stitching. Sometimes you may have seen in cricket grounds and so on, they superimpose an advertisement on the grass. Actually, the advertisement is not there. It has been artificially done. So those are also done using these techniques. Okay, then we'll briefly look at the image formation. What that means is when you have a camera with a lens how the light comes through this lens and makes an image. We will look at that, and briefly about light and shading, and briefly about color. I don't understand color too much, so therefore I cannot describe in great detail, but some description I'll be able to give. Thanks. Then we start the 3D vision. 3D vision is slightly a big topic. So first we have to understand the camera calibration. So use a pattern like that. And the camera takes so many images of this pattern, and then we can find out the internal parameters of the camera. Actually, a camera can be represented using uh, a 3 by 4 matrix using 12 numbers, actually 11 numbers to be exact, and those numbers can be found using these kind of a pattern. So by taking maybe 20 images of that pattern. So this is called camera calibration, and we will understand how to do that. Then we will go to two-wave geometry. What that means is there's this vase object is there, this is the vase, and there are two cameras looking at this same camera at two positions, and how are these images related to each other? That's called epipolar geometry. We'll understand how to do. And without considering of this epipolar geometry, if you just try to mesh pixels, we get a stereo. So you can see this is some kind of a 3D thing. So we will study that also. Then the 2020 work called NERF. So that one, they look at how the intensities must have been arranged along light rays that are reaching different cameras. So using a large number of pictures of this little toy excavator, this JCB or something, and you can make a 3D model of that and you can rotate it. Now, these kind of things are very important. If you want to buy a phone or something, sometimes you go to websites like GSM Arena and you try to rotate the phone and see, right? So 3D rotations are very important. Mm. But those are from CAD drawings. But if you have the object and you want to make many pictures and take a 3D reconstruction, this is one of the ways to do that, called NERF. And then after that, we will look at 3D Gaussian splatting, which is a 2023 work. Mm, how to do that using by locating Gaussians at some of those points. We will look at that later when the time comes. Uh, you need some time to describe that. I just wanted to put a picture of this Wang and others, VGGT. This is a CVPR 2025 Best Paper Award. This is the topmost conference in the world. Computer vision is at the very peak in the world's conferences. This is called International Conference of Computer Vision and Pattern Recognition. So there, you can see it makes large number of images in this scene, and it is able to generate the depth map, and it is able to match these features, and it can do that extremely fast. So this is their contribution. I have not read the paper, but it must be a very, very important contribution. Okay, so after doing 3D vision, we will look at the segmentation. So you can see these video segmentations of the so-called SAM2 model. It's ICLR, International Conference on Learning Representations, ICLR 2025 contribution by Facebook. This this is not actually segmentation. They have done something other than segmentation also. So segmentation means it's very simple. So if you take an input image like this, you can see the input image there. Uh, if you send it to the segmenter, for every part of the image, like the wall here, like the chair here, we assign a label. To represent that label, we have used a color in this image. So assigning a label to every single pixel, meaningful of what we see, is called semantic segmentation. Um, Binary segmentation is simpler than that. If you take this llama image here, you assign black to the background and white to the foreground. Now you have a so-called binary mask now. So this is called binary segmentation. Uh, you can see it is extremely important to do the segmentation, especially in medical image processing. You have to segment the tumors, segment cancer cells, and so on. Okay. Yes. Any questions up to now? Okay. Don't hesitate to ask questions if you don't understand. Don't waste the valuable time that you're spending for these the 2 hours during on a Saturday. Okay. Yes. So some introduction to deep learning for vision. So this is the very research area right now I'm working on. So I have one research area that's computer vision. So we have a good understanding about this. So before that, maybe I will show you a picture from a website. Let me see that. It's good to show that. So you can see this. There is this prize in computer science called the Turing Prize. So this is like the I would say the most important prize in computer science. So this was in 2018. This was won by these three people. Uh, Professor Joshua Bengio, Professor Jeffrey Hinton, and Professor Jan Likun. Um, Likun, yeah. So Jan Likun is with New York University, and also he's the chief scientist at Facebook, Meta. Joshua Bengio, I think he does things. Jeffrey Hinton, uh, you know that in 2024, Jeffrey Hinton won the Nobel Prize. So these are the ones who have seriously contributed to this area. So this first work that I'm showing is Professor Jan Likun's very early work, 1998 work in recognizing handwritten characters like this using a convolutional neural network. You can see he has convolution operations. We will study this in detail when we study convolutional neural networks. What he does is when you get an image of a handwritten character like this, it will produce, this is actually this network is actually numbers, it will produce one of the 10 outputs. So if the output is the first one, it's 0, 1, 2, 3, 4, up until 9. So very simple network, but this was very effective in recognizing things that they write on checks, checks that they are giving to people, right? You have a checkbook, you write a check and give in the US. So this check scanning is automatically done. So this is that network that did that by Arlicon. Okay, so people who were working on deep learning were silently working because others were generally ignoring them at that time. Then a surprising thing happened in 2012 at NeurIPS conference. This is the topmost machine. Okay, in you are doing this AI degree, AI conference. So in the NeurIPS conference, mm, three people were involved in this paper: Alex Krzyzewski, Ilya Sutskever, and of course Professor Jeffrey Hinton. They came up with this so-called AlexNet. Most of you may know about this, and that introduced the convolutional neural networks strongly to the computer vision community, where they were able to solve the so-called ImageNet large-scale visual recognition challenge. They won it by a large margin. This is usually very surprising in the computer vision area. How did they do that? They used a convolutional neural network. Mm. As the title here says, a convolutional neural network. But one thing is, they ran this on two graphics processing GPU cards. You know that computers have graphics cards. Ran it on two GPUs. That's why the network is shown like that in the original paper. Also, the diagram appears like that. This is in the GPU one. This part of the network is in the GPU two. They used RTX 4080 cards. We don't even consider them right now. They are very old, small cards. So this was a 10 class problem, as you can see, 10 characters, 0 to 9. This was a 1,000 class problem, cat, dog, sheep, like that. Actually, car, sheep, like that, those different kinds of image classes, image classification network. So I do not know what Krzyzewski, maybe we look at their pictures. It's good to look at their pictures also. Let's see whether I can get the picture of these three. Yeah, this is the picture. So you can see in this one, this is, I think this is Alex Krzyzewski. This is, I think, Ilya. This is Professor Jeffrey Hinton. So I don't know what Alex Krzyzewski is doing now. But Ilya Sutskever, he became the CTO of OpenAI, which produced ChatGPT, one of the most cited people in this area. So I think he was the brain behind all these generative pre-trained transformer GPTs. And as I said, Jeffrey Hinton won the Nobel Prize. This is one of the most cited papers of all time in human history. It is more cited than the DNA paper. So you can see how influential these things have been in forming the current trends in the world. Yeah. Then after that, there were some other contributions. So maybe we jump to 2016. In 2016 CVPR conference, Kai Ming He and others, they are from Microsoft, they understood how to deepen these networks. If you look at this network has, I think, 1, 2, 3, 4, 5 layers, I think, 5 layers. This network has 8 layers. You can just count them. And this network, they had 34, 50, 102, and 1052 or something. So they understood how to deepen these neural networks. So this is a great contribution. With this, so many advancements came. So now in the area, there are convolutional neural networks. We call them plane networks and rest nets. Rest nets. So it's totally changed. The field totally changed because of this contribution. Yes. But the most important contribution of perhaps just a second to the Alex Krzyzewski's paper, AlexNet paper, is this one, NeurIPS to 2017 contribution by Vaswani and others. Vaswani and others called the transformers. So transformers, they use the so-called attention operation. So I will briefly show a picture later on about what this attention operation means. This was the basis for the work done by Google, and I think OpenAI used that kind of work to do extensive language processing in natural language processing. So these are great contributions. In the latter part of the course, we will understand how the transformer works also. Yeah. So in the deep learning for vision part, we will briefly talk about how object detection happens. Now, this is an early object detector called fast RCNN. This is after RCNN and fast RCNN. They were able to draw a box around the objects. This is not like taking an image and giving it a label like cat. This object detection is different from that. It is, if you have more than these, let's say it's a cat, another cat, maybe a cow or something. Around each of these objects, you can draw a box. So that is called object detection. When you are able to draw a box around the object in the image, that's called object detection. These are object detection networks. So very influential work is this faster RCNN. So we call it a two-stage detector. You will understand later why, because it has a so-called region proposal network and the actual classifier. That's why it's called a two-stage detector. But then after that in 2016, this YOLO was presented by Redmond and others. It's a very famous network. I think many people use that. It's called a single stage detector. Both these tasks are done in one single look at the image. That's why it's called you only look once. You only look at the image once. Yeah. YOLO. We can understand YOLO also how that works briefly. Yes. But now you can see that both these works are prior to the transformer. Transformer paper was introduced in 2017, as I mentioned, Vaswani paper. And the transformer paper was adapted to computer vision in 2021 by Dosovitsky and others in their famous paper called VIT paper, VIT Vision Transformers. So I will not tell you how it is done exactly, but later on I will tell you. They patchify the image, break the image into patches, and then treat each one of these patches as one of those words that are fed to the transformer. So this is a revolutionary network, but there are advancements on top of that also. Then in 2022, also a beautiful thing happened by Rombach and others called in the paper, usually called the stable diffusion paper. It's called stable diffusion because the company is stable diffusion. There's nothing stable in that. So they were able to generate images with that image generation based on a mask or based on some textual input or whatever. They were able to generate images. So these are the images that you see circulating on the internet. I think you may also use Midjourney and other image generators to generate images. Yeah. Yes. So today we will briefly look at we looked at this, and we will look at some ideas about what AI means. You are doing an AI degree. I will give you my definition about that. Machine learning, deep learning, what all these things mean, in my opinion. And I will introduce generative AI also because that's an important buzzword right now, and some vision projects that we have done by the undergraduates in the department. Yeah. Okay. Yes, before I go into this, do you have any questions? So you can, don't hesitate to type or ask. Yes, I hope that all of you are paying uh, keen attention to this. Okay, then I'll move on. So I want to first introduce what image processing means. Yeah, what is image processing? Image processing means you have this image processor here, whatever it is. You give it an image, the output is a modified image. That's what I mean by image processing. So for example, assume that we have this noisy image of Wonder Woman, a beautiful image, and this noise, you can get rid of noise by so-called Gaussian filtering. So this one is an image processing operation. So what you usually do in Photoshop or GIMP, those things are image processing operations. And then let's say this image has salt and pepper noise. Uh, and then you can use so-called median filtering to get rid of that noise. That one is also called filtering operation, although it's non-linear. We will talk about that later uh, when we go through the lectures. Yeah, that is image processing. So input is an image, the output is a modified image. But if you think about computer vision, which is the main topic of this class, uh, of this course, you give it an image, video, text. Output is a decision, a new video, or a new image or new video, because this comprises a decision. It is not actually a modified image. It comprises the decision into it. So in computer vision, we analyze digital image, spelling mistake, or video, analyze digital images or videos to make a decision. Face detection, for example, object detection, semantic segmentation, these are examples. Now think about this, for example. Now here, each of these people have been identified with a different color, and pixels comprising those people have been colored in that. So this kind of thing is called instance segmentation. That means each instance of the person is segmented out. So it's actually the 2017 Best Paper Award at ICCP. Uh, you can see when you give it an image, it will give you a decision. That this person is there, this person number two is there, elephant is there, like that. Face detection. You give it an image and it will draw rectangles around the faces. And then this one also I generated for you this image. I think very young people are there in this class. Maybe some of our students are also there. I used the prompt in Google Whisk to generate an image of a beautiful and serene scene of a young man asking for the hand of a beautiful girl. So what an image, right? So image generation, it's very realistic. Uh, yeah, those are image generations. So you can see all these things belong to the large field of computer vision. Okay. So now we understand what image processing means, and we understand what computer vision means. By the way, there is a quiz that you have to answer. It's on the Moodle. It's totally based on these slides. It's very simple, but totally based on these slides. So it will actually encourage you to properly participate in the class. That's the purpose of that. Okay. Yeah. Uh, Now let me introduce you these terms, what I mean by these terms, AI, ML, NN, deep learning, and so on. So especially the deep learning part. I know that you have taken a deep learning course. Mm. Deep learning is a machine learning advancement that allows the system to automatically discover or learn representations. So we actually call this thing representation learning using a stack of multiple deep layers of neurons, or we call it a neural network. So you can see mm, there is a car, for example. We want to look at the image of the car and try to represent this car using a set of numbers, using a vector. This is learning the representation of the car in some vector space. So this is actually the meaning of representation learning. So you are learning a representation. So in deep learning, we learn the representation using neural networks which have multiple layers. To be more specific, more than 8 layers. When you have more than 8 layers of these so-called neural network layers, we call it deep learning. Actually, if you take the name of the conference, one of the second best, perhaps, the conference in AI, it's called International Conference of Learning Representations, ICLR. So you can see the correct names that they have used. Yeah. So I hope now you understand what deep learning means. When the number of layers is more than 8 of a neural network, we call it deep learning. Okay. Now, artificial intelligence is getting the machines to behave like human beings. And that you can do by looking at data. By looking at past data or present data, you crunch the data and try to learn from this data. Then you call it machine learning. The formal phrase for machine learning is pattern recognition. Then there is one technique that can do pattern recognition well right now. That's called neural networks. So it is within that neural networks. And you know that when the number of layers is more than 8, we call it deep neural networks or deep learning. Generative AI means you learn the underlying probability density function of the data distribution. I will show you examples of this later. When you learn the underlying probability density function of the data distribution, we call it generative learning. So this is the landscape of AI, ML, neural networks, deep neural networks, and generative AI. Any questions about this? Is this clear? Yeah, I hope it is clear. So some disruptive changes that happened is now in 1958, New York Times published an article by US Navy saying something. Let's look at that article. This is that article. Can I enlarge it? I cannot enlarge it, I'm sorry. I think you can see this a little bit better now here. I'm sorry, I didn't download it. So this one says, I'll say what it says. It says in 1958 article, in about 1 year, I think he's talking about the work by Dr. Rosenblatt. In about 1 year, using $100,000, the Navy will be able to build a reading writing machine. Reading writing machine. I think $200,000. Yeah, $100,000 is about a year at a cost of $100,000. But you know, now we have ChatGPT. It can read and write, but it has taken like 70 years and billions of dollars to have been able to do that, right? It has come true, but at a much larger cost of time and computation resources. Then, as I mentioned, convolutional neural networks came into the mainstream in 2012 with the AlexNet paper. And this showed how to use GPUs for parallelization, graphics processing units. I'll show you pictures of them. Then the transformers were introduced in 2017, and GPT, ChatGPT came in 2022. Yeah. So why now? Because people understood that the research work that you do at universities or companies translates, goes into the industry, and you can make money out of that. So therefore, it became very popular. Also, the computational power became available. Now you have great processors like Intel processors and so on. These are nice processors, but their ability to parallelize is quite limited in comparison with graphics processing units like this. This is a gaming card, NVIDIA RTX 4090. We have one card like that. We don't have too much computational power, but this card can do small computations, massive number of them very parallelly, much parallel. Yeah. So these things help the neural networks research to grow extremely well. And now you have NVIDIA H100s, H200s. I think these are like $30,000 each or something. So they're very expensive. Only large companies can afford them. Also, the computational frameworks got developed, TensorFlow by Google and PyTorch by Meta. So in our deep learning work, we will use PyTorch. So these things in collaboration help the field to advance so much. And then there are representations that you can use to put them in hardware also. We will not cover those in class. So I will, with this brief picture, I will show you how these two, the old classical paradigm and the new neural network based paradigm compare. In the old paradigm, we have some kind of an image of a cat. Then we extract the features using handcrafted features. That means we design those convolution kernels by hand and we extract the so-called features. You will understand what these things mean in great detail when you go through the course. And then you have a classifier. I think you may have learned about these random forest classifiers, support vector machine classifiers, and so on. Usually the support vector machine classifier is used for this, and your nearest neighbor classifier, support vector classifier, and so on, and a classifier. So now the classifier will tell whether it's a dog or a cat or something. Then if the image is a cat and the output is a dog, there is a loss. If the image is a cat, the output is cat, there's no loss. When there is a loss, you affect the network by changing in parameters. You actually change the parameters of the classifier. So this is the learning that happened prior to the coming of the neural networks into the field. And when neural networks came into the field, these two blocks joined. And now you have the neural network which discovers the features that are good for classification by itself. You don't handcraft those features, but the network discovers those features by itself. Then, of course, you can see the accuracy must become so much better. So I have put a picture of these AlexNet's features that it automatically discovered. So these features are from the top GPU. These features are from the bottom GPU. So you can see it has discovered things that people also use, like the edges, yeah, edges, the color blobs, and so on. So we use them to think about it. If there's a red color blob and some lines around it, we may call it an apple, things like that, right? So it has discovered the low-level things that human beings also use to classify these images. Yeah. Okay. Any questions? Are you okay? Yeah. Very good. Yeah. When you don't ask questions, I get scared also. Yes. Please don't hesitate to ask questions. Just type in the chat. Yeah. So please pay attention also because the quiz is there. You have to answer that quiz based on what I say. Okay. Now, we will look at the major application areas of this AI field. Computer vision is a major application, as you know. The great examples are Tesla's self-driving car, Avatar 2 movie production. All these things are based on computer vision technologies. Key technologies are convolutional neural networks and transformers. So other examples are defect detection, volume computing applications, virtual reality displaying, self-driving also. Yeah. And then natural language processing is also a very important application, as you all know. Google search, Google's now it's called Gemini. OpenAI's GPTs, Llama 2, 3, and so on, they use transformers. So public chatbots, negotiators, these are examples of those. Then there's another important field that apply these techniques: data analytics, data sciences, Amazon product recommender systems, YouTube's video recommender systems, quantitative finance models of a hedge fund. All these things are data science techniques. And they use these and many other techniques: machine learning, big data, NLP, natural language processing, cloud visualization, all these things they use. Recommendation systems, customer finance, business analytics like done in Netflix and Amazon. These are examples of those. Okay. Yes. Any questions? Yeah. Okay. I'll be very happy if you can ask some question or something or make a comment. Maybe you also know many things about these things. You can contribute. Okay. So now I want to talk about briefly what supervised learning means, what self-supervised learning means, and what reinforcement learning means. Okay. So in supervised learning, we learn from labeled examples. For example, you have cat images, you have dog images. That means the label of the image for whether it's a cat or a dog is available. Because these labels are available, learning is easy. So you can see here is an example of that paradigm. There you can see the strawberry name is there and the image is there. Banana name is there and the image is. So that's why they are called labels. So true label is available and the image. So we give the banana image, for example, to the supervised learner, and it may say banana or some other thing. If it predicts true, it's good. If it does not predict properly, then we let that loss affect the learner and change its parameters so that it learns it correctly. Next time, it will produce a correct output. So this is the training phase of that. So after training is over, we come to the testing phase and we give it an image like a strawberry, then it has to say that it's a strawberry. So we can say this is the testing phase, training phase and the testing phase. Yeah. That's about supervised learning. Now let's look at what self-supervised learning is. I will show you other important examples also in self-supervised learning. In self-supervised learning, we train on unlabeled data by creating its own supervisory signal. Own supervisory signal. Data is unlabeled. That means if you have cat image, there's no label called cat. You just have the image. If you have a chunk of text, you just have the chunk of text. You don't have a label saying, okay, this is an article on the World War or something like that. There are two approaches of doing self-supervised learning: reconstruction and contrastive learning. So maybe I will show you some examples of those later. So here is a pictorial representation of that. Okay. Now think about this. You don't have the labels, but you have the images. So what you do is sometimes you give these exercises to kids, grade 3 kids or something. You have an image. Some parts of that image are missing. So you can see these apples, these parts have been masked or they're missing. So this is a masked image. So what you ask the network to do, like a child, is to complete that. If it completes it well, it's good. If it does not complete it well, it's bad. So you force this network to change its parameters so that it learns how to properly complete it. How can we decide whether the completion or good is good or bad? Because we have the original image. Although we don't have the label, we have the original image. So you can see it's a very powerful self-supervisory signal. Yeah. So this is called the MLM or the mask lang MIM or mask image model. Then after that, what you do is you do fine tuning. That's a question. I will answer that question very soon. Fine tuning. So when you want to test it, that means you want to give a strawberry and get it called a strawberry. You have to add another little bit of a thing to the learned part. This we call this the encoder part, and give it some labeled examples and train it to call as strawberry. This is much easier than the previous task of self-supervised learning. Yeah, there's a question: is unsupervised learning the same as self-supervised learning? Actually, no. There's a subtle but important difference. In self-supervised learning, there is a supervisory signal. There's supervisory signal. that actually changes the parameters of that. That is this proper completion of this image. Not this is has not been properly completed. So therefore, we force the network using that signal to change its parameters. If you think about unsupervised learning, it is like clustering. You have um, bananas, apples, and so on. You just cluster them based on the color or something. Color and the weight. You just cluster them. There is no supervisory signal there. Yes. So that is different, but self-supervised learning is the important paradigm now. Okay, one more very important paradigm now, as you know, is the reinforcement learning. So reinforcement learning is like training a child. For example, assume that training a dog to do tricks. Now you ask a dog to you throw a stick and you ask a dog to pick it. Basically, go to arrange. If it brings the stick, you give it, some little food or something. You give it pankella. You give it, give to the dog. Dog is very happy. He will do it again. If it does not bring it, you hit the dog and you call it a bad dog. So you can see negative reinforcement and positive reinforcement rewards are available. So this kind of thing is based on reward signals, reward signals. So if you have the reward signal, you can get the system to behave, produce the output the way you like it. These are extremely important. So what people do is when they use reinforcement learning, they get a reward system constructed or trained. Reward system constructed or trained. If you think about the ChatGPT, we don't know too much about ChatGPT because they have hidden what they do. In the ChatGPT, they hired 40 people, 40 people to give questions and answers. Questions and answers. Yeah. So using that, they were able to get the network to work up to some extent. Then after that, when the network generates 3 or 4 responses, people rank them. Okay, it says one sentence, two sentence, three, four, five, let's say 4 options. Those 4 options, people rank them. So from the way people rank them, they train the reward function. But right now, I think also you are helping ChatGPT to do that by clicking one or the other when it gives you 2 responses. This one is better, this one isn't. So you yourself are helping for ChatGPT to improve itself by providing this reward signal. Reward signal. So constructing this reward function is the most important thing in this. It is problem dependent. So ChatGPT or the so-called Instruct GPT paper, they use the so-called proximal policy optimization, PPO. That's also by the papers by OpenAI. I have the PPO paper printed because I had to read it for something. This is the PPO paper. It's an extremely interesting paper. Mm, Obviously, it worked. And then in 2024, DeepSeek came and tried to revolutionize this field. You cannot DeepSeek came. DeepSeek uses GRPO, Group Relative Policy Optimization, for robot navigation, for large language models, all these things. This reinforcement learning is used. It's expensive to do, but it's very powerful. Yeah. So one more question, what does it mean by supervisory signal? Is it the same as supervised training method or is it different? Supervisory, yeah, it's a very good question. So in the supervised way, you know the label of the uh, banana. It is banana. You have the label. But you see in the self-supervised one, you don't know the label. So supervisory signal is whether you properly completed or not. That one we understand, right? Yes. So I will show you some other supervisory signals also later. They are not the same. Supervisory signals in self-supervised learning can be automatically extracted from data itself. That means you don't need human beings to manually label them. That's the advantage of that. That is why people were able to train massively data-hungry systems like Gemini, GPT-3, GPT-4, and so on, because they were able to use internet scale data. These things can never be labeled. Maybe like, so I hope you understand these important concepts. Yeah. All right. So now let's once again go back to the 1958 and try to understand how this perceptron thing worked. Thank you for those questions. I am very happy about that. Okay. Uh, Now, let's think about an image. Assume that this image has, it's a 32 by 32 image, 32 by 32 image. That means 768 pixels, 32 by 32 is 768. Assume that. So now we have this D is 768. You take all the dots in the image, we call them pixels, and give it to this neural network. And you have W1 to W2, these are weights. We call them weights. What you do is you take this number, 200, 150, like that, this pixel, value of that pixel, you multiply it by W1. You take the second pixel, multiply it by W2, and you produce this function Wx plus B. So we represent it as Wx plus B. You can see what it means, like W1 x1, W2 x2, W3 x3, like that, or that one. And then you get the sign of that. If the sign is plus 1, you call it a dog. If the sign is -1, you call it a cat. So very simple, right? This is the perceptron, which Rosenblatt sort of discovered a similar one. Mm, mm, mm. So, uh, people were very excited when the perceptron was there. They thought, okay, how the human brain works, now we understand. No, yes, because the neurons also, like when you look at them, they looked similar to them. Yeah. But unfortunately, people found that this can only do linear classification, as shown here. What that means is this. So if these are cat images, if these are dog images, assume that they are not 768 dimensional, but only two-dimensional. Assume that for the time being, only two dimensions are there. You can separate using this network only by drawing a line, linear line. In 2D, it's a line. In 3D, it's a plane. In 4D, 5D, 768, it's a hyperplane. So these networks called perceptrons can only classify using a hyperplane separating plane. Separating surface is only a hyperplane. So when the people realized this, they felt very bad. Oh my goodness, it's a linear classifier, totally useless. But fortunately, people found that by connecting more than one layer, so-called having a hidden layer like that in output plane, with so-called non-linearities, this is a plus or minus function. Okay, this plus or minus function is what I have shown by this little this step symbol. If you have a non-linearity, then you can get a non-linear separating hyperplane. Non-linear separating surface. Yeah, so now you can see these are multi-layer perceptrons or densely connected networks. So, uh, mm, it is possible now. So therefore, once again, it's possible to do something, but people did not generate interest in neural networks very quickly. Okay, now let's look at one of these linear classifiers in slightly more detail. Actually, we will be able to get this running later on your computers or in the Google Colab and actually see that this is working. One more question. What are the computer hardware requirements for running an image processing application only GPU? That's a good question. Actually, for simple image processing operations that we will do within 3 or 4 classes, your computer is more than enough. But when we come to deep learning, for simple examples, your computer or the Google Colab will be enough. But if you want to do slightly something complicated, then you will need access to graphics processing units, GPU hardware. We have some of those things, but you can rent them also. Uh, Thank you for those questions. Let's look at this now. Now, I said that this cat image will be, I mean, this is a color image, okay, 32 by 32, let's say. Color. So that means three colors have to be given to RGB. So therefore 32 times 32 times 3. I think 3072 or something. Whatever it is, whatever that number is. That many pixels are there in this cat image. Okay. A very bad looking cat. Very ugly cat. But for the time being, assume that you can represent that using four numbers. 1, 2, 3, 4. Because I want to show it to you. Okay. Four numbers. So each of these four numbers will be multiplied by this, this corresponding to the cat score. This, and this corresponding to the dog score. And this, and this corresponding to the ship score. Okay. So what that means is 0.2 multiplies 56, minus 0.5 multiplies 231, zero point 1 multiplies 24, and 2 multiplies 2. And then you this at this number called a bias. And then you get minus 96.8. And then for the dog score, that means this light green row, you get 436.9, 37.9. For the blue one, that is ship score, you get 61.95. Right now, what is the class? Is it a cat, a dog, or a ship? People are typing answers. The answers are correct. Thank you very much. It's a dog. Why is it a dog? Because the dog score is very high, right? Dog score is very high. Why is the dog score high? Because this W has not been tuned and this B has not been tuned. That's why the dog score is high. So therefore, what you need to do is, because we know the actual labels, this is a labeled linear classifier, this is a supervised learning. When it is making a mistake, we say, okay, these things have to be recorrected. These have to be recorrected. You keep on correcting them again and again and again. After that, it will hopefully produce the correct label. It does. But the beautiful thing is not only that. The beautiful thing is, after you do this thing, and you take this, for example, let's take this one, dog score, ship score, something like that, a car score, like that, many of them they are. And I said, this is, although we represent using four numbers, it's a large number of numbers. You arrange them like an image. If you rearrange them like an image, the car row will look like an actual car. The bird row will look like an actual bird. The cat row will look like an actual cat, blurry cat. Yeah, so this is amazing. So you will also be, now if you take the horse score, the horse row, you will look like a horse looking this way and that way. Because in the actual images, horses were looking left and right both. So you can see a linear classifier learns the weights. But how do we learn? This is a part of this course, and we learn that through so-called backpropagation. Backpropagation is actually gradient descent, which you have done, in the past. So if you go to a mountain top, how do you go to the bottom of the valley? You follow the highest slope, steepest descent. So this is called gradient descent. Actually, these networks, they do gradient descent. Now, if you take PyTorch and TensorFlow, if you ask me to define them using one single word, what are they? They are gradient computing machines. So they do autograd operation. That means automatically they can compute the gradient. And when you have the gradient, you can do gradient descent. So we will look at these things when we get into this learning part later on. Yeah. A question, what is the reason behind generative AI models being able to generate accurate images of well-known people, but not those who are publicly represented? Um, uh, Yes, that's a good question. So why is it able to, for example, generate a beautiful image of maybe Taylor Swift or something? The reason is these have been trained by images now. So when they have been trained so much by these existing images on the internet, they have mm, uh, for the time being, let's say for easiness, let's say they sort of remember some sort of a notion of that. So that's the reason. Yeah. Mm. Yes. There is something more. Maybe you will understand a little bit if when I talk about the vision language models later on. The textual representation of that person when we say, for example, Taylor Shift. Taylor Swift's textual representation should match with something, right? So those matches have been established when you have large number of images of that person on the internet. I think that is the reason, although I exactly do not know the very reason for that because I don't have too much experience in image generation. Uh, any other questions? Yes. So can you explain how to derive WX from images? This is very important thing. Now, generating X from the image, uh, if I take the full image size and arrange all the pixels also, I can get some X, but it will have many numbers like that. So let's compute that. If you assume that your image is 32 by 32, because it's color, there are three planes, okay? 3, 32 by 32 by 3. So the size of that will be Xi will be 32 times 32 times 3. That means, I think 3072. 3072 numbers. So here I have put 4 numbers, but actually this will have 3072 numbers. That's one simple way of doing that. One simple of generating X. But there are other ways of doing that. You can send this image through some network that knows how to represent that network image and generate a smaller set of numbers, like 500 numbers or something like that. These kind of techniques people actually use. Now that's about X. X is the image. But how about W? So W we initialize using some random numbers. So that initialization also has some rules. So timing initialization, this, that, and so on. Now we initialize them with random numbers. After that, we use the backpropagation from this error, backpropagation to or gradient descent to adjust that. That's how the W's and B's are finally computed. I hope that this is generally clear, but you do not fully understand that because we have not done that, but hopefully we will do that later. Okay. So that's about the linear classifier. Then we said that there are so-called convolutional neural networks. They are not just linear classifiers. They have other computations by running many small kernels. I know that you do not understand what that means yet, but watch this one. This is an animation from this. So you can look at it. So here, if you select ladybug or pizza or something like that, the corresponding tiles, they sort of get activated. These are outputs of those convolutions. You can see, and then finally, on the right-hand side, the corresponding class gets activated, right? School bus, and so on. So I ask you to please at home go to this website and watch this properly. There are many other things to learn. I don't want to spend time in telling you how these connections happen and how these numbers are computed, how the convolutions are running internally. This animation has that. So please look at it. So this is how convolutional neural networks work briefly, but we will understand how they actually work by doing our own little programs. Okay. Then after that, linear classifiers, the convolutional neural networks. Then after that, the attention or the transformers. I want to give you a brief idea about what this attention means. Here you can see a sentence. You cannot see the sentence now. Here you can see a sentence. And we have highlighted the word it. The animal didn't cross the street because it was too tired. What does it refer to? Okay, you will all, because you know, because you are human beings, you know how to attend to words, you will say it refers to the animal, not the street. So these are, thank you. This has higher weight, higher attention strength. But if you take this sentence, the animal didn't cross the street because it was too tired, this it refers to the street. This it refers to the street. So you can see, depending on the context of the sentence, the same word it can attend to the animal or the street. So you can see the context of the sentence is there. So this is the very uh, concept that transformers use. Their main operation is attention. So using this attention and many other computations, transformers are able to understand or have language understanding. Yeah. So later on, if you ask me, I can show you a few things later in the class, in other lectures, how these things actually work. Yeah. Okay. So now, because everyone is talking about generative models, so I will show you the accurate picture of what they actually mean. Generative pictures, um, generative models. Okay. Okay. Now think about this. Now, this is a probability density function. We call it a PDF. Right? Probability density function. What does it represent? It represents that this region, dots in this region have very high probability. Dots in this region have some probability. Dots in this region have zero probability. Okay. So think about this now. Think about a distribution of people in a school. People with height 143 centimeters, let's say. You have so many, right? So if you to take a person from a class, it is very probable that this person's height is close to 143. So if you sample from this probability density function, the chances are high that it represents the characteristics of that population. What doesn't it represent? If you take a class of students, it does not represent the height of dogs. Dogs are very short in height, right? Dogs. Some dogs are there tall, but so therefore, if you have the human class and you have the probability density function of the heights, if you sample a point, it will represent a human being's height, not a dog's height. So here we have learned the probability density function of the data. But these are one-dimensional data points. Then you can go for, okay, I'm showing the sampling, two-dimensional data points, two-dimensional. So if you sample from that, you will sample a point that represents this probability density function once again. But data is not just one-dimensional or two-dimensional. It's massively high-dimensional. If you take an image, we saw that it's 3072 dimensional if you take a 32 by 32 image. So in that space, 32 by 32 dimensional times 3 space, I forgot to write 3 here. I should write that times 3 times. If you sample a point, you should see an actual image. If you sample the first one, if you got an actual height, if you sample a point from the distribution that represents images of 33 by 32 by 32, you must get a matrix that looks like an image. This is generative learning. You learn the probability density function of data. So if you sample this point, maybe you will get a ship or something, car, this area sheep, this area horse, and so on. But if you sample from outside, maybe you will get noise. That does not look like an image, something that does not look like an image. So this is generative modeling. So building a probability density function of the data. So this one you can do with several ways. So in summary, generative models learn the underlying distribution of data. Once learned, they can generate new data samples that resembles the training data. So someone asked about why, if you take an image generating model, it is very easy to get Taylor Swift's images. It is because it has learned from data the probability density function, but it does not have the probability density function representing someone, maybe one of our actors or actresses in Sri Lanka. Yeah. Okay. So if you take generative AI, these applications are text generation, generates AI from generative pre-trained transformers, for example, can generate human-like text, chatbots, Gemini, ChatGPT, all these things. So you can see this model has learned the probability density function of words that can appear in among all other words. Then when you give this set of words that came before that, the probability of the next word, the model sort of knows. So therefore, highly probable word comes out. Yeah, that's autoregressive generation of words. And then image and video generation can be done. So stable diffusion, I showed some paper earlier, Mid Journey and so on. I showed an image also. Then data augmentation, music composition. So like that, there are many applications of generative AI. Okay. All right. Now I will go talk about BERT. This paper is by Google, but Vaswani paper, the original transformer paper, was also by Google. This BERT is the one that drove Google search for some time. I do not know now. Now this one is now we looked at a masked image model, the incomplete banana you give when the model learns to complete the banana. The problem with these natural language processing systems or language generators is it is not possible to label internet scale data. So you have to derive a self-supervisory signal in this. So the self-supervisory signal we are going to understand now. Now let's take a sentence like this. This is the class signal. Forget about that. Let's stick to improvisation in this whatever. So what we do is this word we mask. We mask this word. This mask. It blank. So in grade 3, 4 also you did this, right? The teacher gives I blank apple. Then you are supposed to put that word in, right? I ate an apple, right? I blank an apple. I ate an apple. Fill in the blanks. This is exactly that. But you know the actual sentence. You know the actual sentence. So therefore, if it does a good job in finding this masked word, it's good. If it does not do a good job, we know. We know how to change the parameters based on that. Now, in English, maybe there are 50,000 words. So this network will produce probabilities for each of the 50,000 words starting from aardvark to zizizwa. So hopefully the improvisation, that is the correct word here, that probability hopefully will be high. If it is high, that's good. That's the correct word. If it is less, then you have to change the parameters of the network using so-called backpropagation. So you can see this is the masked language model that drives Google BERT and OpenAI's other models and so on. But in addition to that, this had some other things like next sentence prediction and so on. If you have questions, I can describe about them, but that's okay. We can ignore for the time being. So this is what how a masked language model works. They randomly mask 15% of the tokens. We call them tokens. They are slightly smaller than words in size. Use the output of the masked words question to predict the masked word. That's it. That's it. This is the BERT paper. So now you can see why Google is very unhappy about OpenAI using their papers and start making money. Google opened up all these papers, but OpenAI, although they call themselves open, they have closed their knowledge from the world and they are making money. Okay. So after you learn this bird thing, after you learn this thing, which is a huge thing, they can use it for other tasks like question answering, next named entity recognition, and so on. Maybe some of you have done natural language processing course. Maybe you understand what these things mean. Even if you does not, this is a question answering. You give a question, you give the answer, and so on. Yeah. Okay. All right. So exercise for you. A brief exercise for you. What is hidden in this image? What is the actual image? It's a banana, pair of bananas. Mm, thank you. Which one is this? It's a polar bear. Okay, a difficult one. What are these images? There are four images. Can you look at them and discover? A clock bust. Oh my goodness. Oh my goodness. These people, you have that power in your mind to uncover masked images. Yeah, this is correct. This is correct. So this is exactly what we asked these images are exactly from the MAE, masked autoencoders paper by 2000, on 2022 paper by Kaiming He and others. They gave this task to it and they asked it to learn this. So you can see this is a supervisory signal derived from images themselves. No labels are required. So they asked it to complete, and when the network learned to complete it, the network understood what images means. Yeah. Okay. So this is a picture of that paper by Kaiming and others. So we knew that ResNet is also by this author. So you have the mask image. Many blocks are masked. So unmasked, once you give it to the so-called encoder, we will hopefully know what these things are later on. And then the decoder is supposed to predict them and discover the target. If it is matching, that's good. If it is not matching, then we change the parameters. If it is matching also, we change the parameters. So whatever it is, we change the parameters of the encoder and the decoder. So there are other things to this paper. Encode is large compared to the decoder and this, that, and so on. And it's a very interesting paper to read. Slightly hard to read for you right now, but later on you'll be able to read and understand. So before the break, give me a 3 more minutes to show you the other paradigm of learning from self-supervised signals, the contrastive learning. Uh, so this is generative reconstruction. This is reconstruction, right? You mask the image and that part you want to reconstruct. The second paradigm of self-supervised learning is contrastive learning. So these are beautiful images of golden retrievers. These are beautiful images of a beagle. You can see the golden retrievers are close by and the beagle is far away from the golden retriever. So this encoder thing is there. It generates this vector or the representation of the image. And in that space, we want to make the beagles, the golden retrievers come closer, and beagles we want to make far away from the golden retrievers. So this is the contrastive learning paradigm. Bring together representations of similar examples, push apart representations of differing examples. By doing this, you are once again able to learn the network, learn the encoder. This is the so-called contrastive learning paradigm. See, these are supervisory signals that you can get even if you do not know the labels of these images. Here, a little bit question. Okay. All right, let's take a break here. So I will post the recording. In about 10 minutes time, we can uh, uh, meet again. Okay, we'll come back. I hope you had a break. I had a break myself. I need something, but no tea to drink. Okay, so it's start. So there's a question: does learning from supervisory signals, would it be enough to do downstream tasks like classification on in images, or do we have to fine tune using smaller label dataset? We have to fine tune using a smaller label dataset. Maybe there are approaches that somehow manage that, but as I know, in general, you have to fine tune using a smaller data set. Yeah, thank you for that very important question. So downstream tasks are tasks that we want to get done, like classifying an image, segmenting an image, and so on, object detection, and so on. So the initial part is done. So I will briefly show you the books that I can use, that you can use if you wish. You are not required to use these books, but I will teach everything. But if you are interested, this Gonzalez and book Woods is a great book on image processing. Computer Vision by Forsyth and Pons, second book that's combines computer vision and image processing, but mainly on computer vision. This one, computer vision, is slightly research oriented. It's a slightly new book. And then Milan Sonka, it's image processing computer vision. Uh, yes. Then one thing about the conferences and journals. Mm, if you want to read something about this and if you want to do a project or something, you have to pick papers from these good conferences. CVPR is the topmost conference of all conferences. ICCV, ECCV, WACV, BMVC, and ICIP. International Conference of Image Processing, British Machine Vision Conference, WINT Applications in Computer Vision, European Conference of Computer Vision, International Conference of Computer Vision and Computer Vision and Pattern Recognition. In other conferences, the quality of the material cannot be guaranteed. Please know that. Of course, these are computer vision conferences. There are great AI conferences like Neo IPS, ICLR, ICML, and AI. So those material we can trust, others we have doubts. The journals in IEEE transactions on pattern analysis and machine intelligence, PAM, International Journal of Computer Vision, pattern recognition, transactions, image processing, IEEE cybernetics, computer vision and image understanding. These are great. There can be others, but these we can trust. If you want to ask me about questions about these sources, we can talk about them later. Okay. So tips for successful completion. So think about this not as an exam or something that you have to do for this MSc program that you're doing. Think about I want to solve this computer vision problem. How do I solve it? What are the tools available? This is the kind of thinking that you should have. Uh, I will also be very interested to teach in this fashion because I actually asked this question when I was asked to do this question. Why should we do online teaching? Students don't truly or fully participate, but they insisted that. But if you have this in mind, I think you'll learn something, your valuable time, you will make use of it. So please attend all the lectures so that you can ask some question. Um, of course, the videos will be available, but if you can ask a question, get something clarified, you will engage. Go through the material the night before, spend 10 minutes, 15 minutes to flip through the slides so you remind yourselves what we did this week for the next week. So from next week, it will be possible for you to write a small piece of code. Then you will feel so enthusiastic in class if you write a small piece of code and get some image change or something like that. Yeah. That's a mindset. So we use Python for this. If you do not know Python, uh, can we have a little thing? Is there a person who has absolutely no clue about Python, or are we generally okay? Maybe I'll ask using a poll. Let me try to run a poll and ask how many people know. Can you answer this, please? So that we know how many of you know Python. You will have to learn a bit of Python. Uh, I think in 3 hours you can learn what we want from Python. So if you do not know that, this website will be great. I think know that the inclination is for you to go and watch a video, but it's this one will be much faster than watching a video. This link. So I will send that. Uh, One thing that if a class rep is there, one thing that you can do is to create a mm, mm, oh, there was a separate module for Python called Programming Essentials in AI. Oh my goodness, this is excellent. Yeah, then you have this knowledge. But if you want to refresh, maybe you can go through this tutorial. I'm very happy about it. Oh my goodness, yeah, I didn't know this. Okay, yeah, okay. Yeah, this I was answering, so that's very good. I'm very happy about it. Okay, some websites. Mm, Computer vision software companies, these are large companies. If you want to implement something industrially with a serious budget, you can look at these websites. Industrial camera websites, Basler, Fleur, and camera catalogs can be found here, and so on. Okay, so here are some projects that we have done at the department. These are done by undergraduates. This was by Osudha Jaising and others. He was the island-based in Airways. So they had a, traffic sign and traffic light detection system in a device. And you can see that their system is able to detect all the traffic lights and their status also. And they have a database of all these Sri Lankan traffic signs also. So you can see the paper here at the bottom, this one. This one also is by them, Swift Lane. So this is for lane detection. In self-driving, it's very important to be able to detect lanes. So we have a Sri Lankan dataset and lane detections very fast. This is also a great computer vision project by Aditya Dias and others. He was also the island-based. So island-based, they are in our department. So this is a collaborative robotics project. You can see there is a camera on top. This camera observes this arena. This arena has three robots, this one, and this one. Because of this Aruba markers, you can see where these robots are. And these are bricks, Gadol. So we give building plan to the system. The robots learn by themselves using reinforcement learning to make a building. So mobile robots, they will bring the bricks and the stationary robot arm will pick them up and keep the bricks to build a building. It's a great project. You can see it's a complicated project. And this is one more project that was done by an MSc student called Kaushalya. So she's the first author of that, and a large number of radiologists. These are consultant doctors who scan bodies they do. So this one is like magic actually. So we get three ultrasound scans of the liver. You cannot identify the liver here. I cannot, but Kaushalya now can identify the liver. So then we use the segmentation network called the TransUnit. It's an existing one. And then we get the segmentations of those the liver in these three images. And then we compute some through this parameter regression multi-layer perceptron. We compute the so-called shape parameters. And the shape parameters are constructed, so you don't have to know use what these are exactly, but these are some numbers. They can walk the general model of the liver shape that we construct using CT images. So as a result, we are able to get the 3D reconstruction of the liver using just three images. This is amazing. So then our volume estimates of the liver are more accurate than the general methods that radiologists usually use. Yeah. So it's a great thing. The results. I can see everyone knows Python. Yeah, if you do not know Python, spend a little bit of time, 2 or 3 hours to learn the basics. Basics are enough. Okay. So here is a quiz. So let's attempt the quiz on the Moodle. Does everyone know how to access the quiz on the Moodle? If you have a question, please ask me. It's very easy. So I will tell you most of the answers and then you can write it down. Question number one, you can click in the Moodle. What is the primary difference between image processing and computer vision? We covered this in the class before. So what's the difference? So in image processing, you give an image, the output is a modified image. In computer vision, you give image, video, text, the output is some kind of a decision, some kind of a decision. So therefore, the correct answer is what? Obviously, is not correct. Image processing needs machine learning. Not correct. Computer vision converts and looks in the doesn't. Not correct. Image processing used only in photography. Computer vision used in robotics. Not correct. So A is the correct answer, right? Okay, so please do the answers in the Moodle. So those are counted for the final evaluation. You can say I cannot give you homework assignments and mark them. I can give them, but because ChatGPT is there, you can get all the answers from that. So giving homework is useless for a final summative evaluation. Second question, what's the answer? Okay, people are giving answers. Which of the following is an example of a computer vision task? Histogram equalization, that's an image processing task. Wrong. Gaussian blur, image processing, wrong. Semantic segmentation, yes, it is a computer vision task. Image sharpening, wrong. Padding, wrong. So these are producing just images. This is not even an image processing operation. Third question. What is the goal of early vision in computer vision pipeline? Compressing videos, wrong. Extracting high-level semantics from semantic is a meaning from images, wrong. Creating 3D point clouds, wrong. Extracting low-level features like edges and textures, correct. Rendering synthetic scenes, wrong. So D is the answer for this question. A is the answer for this. I hope these are clear for you after the discussion we had. Okay, next set of questions. Question number 4. Which of the following best describes the structure of this course? What a question, right? It focuses entirely on deep learning for image generation. Wrong. It includes image processing, computer vision, and recent vision methods. True. It is limited to classical image processing. Wrong. It covers any industrial inspection. Is wrong. It is a hardware-oriented course. Wrong. So it is B is the answer. Which of the following recommended successful course? Memorize all the equations before exam. Implement at least one algorithm before the next class. Avoid reading papers, just follow lecture notes. Focus only on coding assignments. Use MATLAB and ignore Python. Wrong. B is the answer. What is an advantage of using Python in the course? It requires no coding knowledge. It is optimized on image compression. It supports dynamic computation graphs and deep learning libraries. That's the correct answer. I did not describe that in class. It is a hardware simulation tool. It only works with C++. Wrong. So please do these answers in the Moodle. Okay, maybe I will go to the Moodle and see whether you are doing it. Yeah, people are answering in progress. Yeah, okay. No, some people have gotten all the marks. Okay, that's good. One more question. Could you please explain a little more about the high-level semantics and low-level semantics? Actually, I do not know the answer to that question. How to semantics means something that human beings understand that you see in images. So, for example, if you see an image of a dog, football, and a man, identifying the football region as football, it's a semantic information, right? That's something that you cannot just detect from color or something, but it has human beings understanding. High level semantics and low level semantics, how to distinguish them, I do not know actually the proper definition. Thank you for the question, but I do not know actually. Okay, let's look at the question number 7. Uh, which of the following is a real-world application of computer vision? Applying a median filter, smoothing an image? That's wrong. Detecting faces? Yes, that's correct, right? Face detection definitely is computer vision. Printing high-resolution images wrong. Converting RGB to grayscale wrong. Saving images in compressed format wrong. What is an example of generative model in vision? Histogram matching wrong. Optical flow estimation wrong. Diffusion models, yes. This is the way images are generated. Sobel edge detection wrong. Bilinear interpolation wrong. Yes. So these are some of these you don't even know yet, but that's okay. Question number 9. Which of the following is a typical use case of segmentation in vision systems? Enhancing the brightness, estimating motion of objects, detecting boundaries between different regions in an image. That's correct. Converting images into JPG format and color grade to grayscale is the correct answer. Finally, what is meant by the self-supervised pre-training in deep learning in vision? Training a model on random images from the internet. Learning from labeled dataset with minimal supervision wrong. Supervised training using multiple GPs wrong. Using reinforcement learning on trained vision models wrong. Learning meaningful representation unlabeled data using a surrogate tasks. That's correct. So the two surrogate tasks that we looked at were, I did not describe them as they are, the master image model and master language models, MLN and MIN. So these are the answers. I hope that you can get all full marks for this. But next time, maybe you will not get the full marks. I think you have 2 attempts for the quiz. So you can, if you don't get the answer, correct it again. Do it again. So I'll give you 1 or 2 minutes to. See how many people have answered. Yeah, a lot of people have answered. Uh, okay, so we will continue uh, to the next lesson. I'll put that in the, wait a minute, I have to put it in the Moodle. That in the Moodle, I'm sorry. Okay, this is the next lesson, so I will give a title later. All right. Okay, can I proceed? Or if there any question or something? No, right? We can, I will proceed. So now we will start with the basics of image processing in this one. So I will show you some pieces of code also. They're very easy. Then we'll be able to slowly build up our ability to get an image processed. Okay. So what is a digital image? A grayscale digital image is a rectangular array of numbers which represent pixels. Each pixel can take an integer value in the range from 0 to 255 for an 8-bit image. So each number is represented by 8 bits. 8 bits means 8 ones or zeros. So therefore, the maximum number that you can represent is 1, 1, 1, 1, 1, 1, 1, 1. That's 255. If the image is a color image, then there would be 3 such arrays. The size of this array is actually the resolution of the image. For example, 3712 times 5568 if you take from a expensive camera. We take top left pixel as a 00 pixel and vertical axis as the y-axis. So this is the picture of what we have described here. So the vertical axis is the y-axis, and you can see the horizontal axis, and this pixel, we call it the 2, 3 pixel. Remember, it's not the 3, 2 pixel, 2, 3 pixel. This axis is the first index, like in a computer language. Yeah, I hope it's clear. So this is a grayscale image, but if you take a color image, you can consider that there's another axis or something, but there are 3 such planes: the uh, blue, the green, and the red plane, right? We call such an image as a BGR image, blue, green, red image. If we access pixels locations such as 2, 3, we will generate 3 values: the B value, the G value, and the R value. Each value is in 2 to 255, 0 to 255. In this context, there are 2 to the power of 8, 2 to the power of 8, 2 to the power of 8 different colors. 2 to the power of 8 is, 256, right? Including 0 is 256 numbers for each value of 8-bit. That's why this many colors can be represented. Okay. So if you think about image resolution, the number of pixels of an image, width and the height, we call the image resolution. This is related to the size of the sensor in the camera, the CMOS sensor or the CCD sensor. If you take, for example, if you take the so-called full HD, that's 1920 times 1080, it has 2 million pixels. So this impacts the image detail and sharpness. If you don't have a high resolution, your sharpness is not there. And the file size is large when the resolution is high, and the processing time also increases. But there's another concept called that's per inch. And so when you print, you have to decide for a square of inch, how many pixels do you print? So for this, from top to bottom, now it is 1 inch, okay? It is 1 inch by 1 inch. In this case, how many pixels do you print? So if you print 300 pixels, we call it a 300 dpi, 300 dpi. So if you take a image, let's say you take an image of 3000 for convenience, 3000 by 3000. And if you display that or print that image at 300 dpi, dots per inch, uh, its height will be 10 inches, its width will be 10 inches. 10 by 10. But if you print it at 150 dpi, height will be 20 inches, width will be 20 inches. But then you will see a little bit of dots. Now, for a good print, you need 300 dpi or more. But for display on a screen, you don't need that many dpi, slightly less than that. So that's why sometimes the screen DPI ratings are 72 to 96 or something. But if you take a phone, a new phone and so on, they will have much larger than that. So for print, you need this. Okay, I hope the difference between image resolution and dots per inch is clear for you. Okay, now let's start a little bit of coding. We use OpenCV for that. So I will explain what this code is and then show you how to do that in Google Colab. Later on, you can start using Visual Studio Code or something, whatever you like, PyCharm, something like that. So we have to import CV2 as CV. So for that, you can see, actually you have to install this OpenCV library. Uh, and then we sometimes need NumPy. Maybe you have used that. And to display things, you need matplotlib.pyplot as PLT. These three lines you anyways need. Okay. Now this is a creating of a 6 by 8 grayscale image. Okay. We said an image is an array and each array's number must be a 8-bit number. And those numbers must be positive. So that's why when we say, when we are creating an image, IM equals, we are using numpy np.zeros, an image of all zeros. Height is 6, width is 8. 6 by 8, you have to put them in parentheses. Data type, you have to say np.uint8. Uint8 means unsigned integers of 8 bits. And then what we do is we take the pixel at 2, 3. This is 2 and this is 3. And set white to that. White is 255. 255 corresponds to white. See? And then we have a little bit of things to do displaying. Figure, comma, ax equals plt dot subplots 1, 1. You just have one subplot. Figure size is 618. I don't know why. Then we take this axis im show, im, and we have to give the so-called color map. Color map is gray, otherwise Matplotlib will show that in color and we'll get confused. Minimum value is 0, maximum value is 0, 20 to 255, that also we say. Tick positions, we want to put these numbers here and numbers there. That's a line here. And then finally, plt.show. Okay, now I want to do that in Colab. And then we will see how to do that in Visual Studio Code later. Okay, so I hope you are ready for this. So you open Colab. What I opened? Colab. Google Collaboratory. So I say new notebook. Okay, so I think I need to install OpenCV. So, but let's say import CV to as CV. So let's try that. It works. So it's there. So I don't know in your machines what happens if it is not working. Let me know. So maybe you can so the ET. I always forget this course number. 5437. 5437. In class. Let's say one in class. In class, okay, let's put the date. Right. So it's very clear what we did. So in mouse sensor advanced computer vision use like a simple mouse sensors. That means the optical mouse, right? I think they just compute optic flows. Optic flows, the something other than something's moving. There's no advanced one, I think, in a mouse. Import numpy. Okay, so this knows no, but I want to type numpy as np. Import matplotlib pyplot as plt. Okay, these things have been imported. It's done this and it's done. Okay. Now I want to create that image im equals. Do you remember the code? np dot zeros, an array of zeros, np dot zeros. And I had to give the size is 6 comma 8. And I had to give the 6 comma 8. I have to give the data type. D type is u in np dot u int 8. Done. Okay. Then I will say im 2 comma 3, that location I will put 255. That part is done. I will give a little bit of time for you to code this on your own. So please start and code. Now we to display this big comma x equals elp dot subplots. Okay, it's already done the code there. So I want to do this the way I did that in the thing. And I want to give the minimum value and the maximum value also. ELT dot show. Yeah, see, this axis thing I forgot, right? Forgot to put the axis at the top. AX or axis set tick position stop. I don't remember, but I don't want to get it from the dot x axis. So the tick positions will come to the top. Yeah, this is exactly what we wanted. So we have set this pixel to 200, 255. If you set to 150 or something, it will appear gray, right? 100. See, I hope this agreed. Okay, so please do this, and I know it is a very simple exercise, but I think it will be helpful. So you can see we go with very simple examples. මුල සිට සරලව. So I hope you have been able to get the code working. So if not, please let me know. Please let me know whether the code is working. If it is not working, please ask me a question or something so that maybe I can look at your screen and tell you if there's a problem also. Yeah, a lot of people are saying the code is working. That's very good. I'm very happy about this. Oh, this is excellent. Everyone is thing is working. So those who have been unable to get the code working, if you show me your screen, share it, then we'll be able to see why, and also others will also learn from that. Yeah, in the poll, a lot of people are saying so. If someone needs any help, don't hesitate. Uh, Let me know. I will help you. NP06 question. What is the meaning of D-type NP uint8? That's a very important question. What this means is each pixel is represented by an 8-bit unsigned positive number. That's what it means, right? So this 8-bit number, so it was something. Um, these are 8-bit numbers. What that means is you have 8 slots like that. So smallest number is 0, 0, 0, 0, 0, 0, 0, 0. That's equal to 0. And the largest number is all ones, right? These are binary numbers, all ones. All ones, 1, 1, 1, 1, 1, 1, 1, 1. So what that means is this is all ones, 1 plus 2 plus 4 plus 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. When you add all these numbers, you get 255. So you can see the value of unsigned numbers, right? There's no sign, all are positive numbers. And uint8. So therefore, we use a small amount of memory to represent one pixel because there are a large number of pixels. Yes, I hope it is okay. All right, that's good. And I'm happy about your ability to get this thing working. Uh, Now let's go to the next one. A color image. a color image. So when you do a color image, so this one is 6, 8. Color image is 6, 8, 3 channels, 3. That's all. But when you set the thing, cannot set just one value. You have to set the three values. B, G, R. Okay. R in this matplotlib thing, R, G, B. Yeah. So let's do that. Color image. Maybe here we have to write a comment, right? Scale image of size 6, 6 times 8. Yeah. Now we're going to get the slide plate. Let's do a color image of 6 by 8. Okay. So I'm going to, shall I do the bad thing of cutting and pasting? No, let's type it, right? Let's type it. Import for OpenCV, CV2 as CV. Is importing OpenCV. Okay, now this stupid guy, this guy knows everything, right? It knows everything what I'm trying to type. Import numpy as np. Import matplotlib dot pyplot. I am typing everything as plt. See, I'm not lazy. Image im equals np dot zeros. I'm exactly typing what it's giving. 6 comma 8. That's the size of the image, and 3 planes color planes. And the d type equals np dot uint 8. Okay, done. It's done. So now I will say im 2 comma 3. That location should get, yeah, this is red. So this one I will copy. Okay, that's fine because it's fair enough. No. So this will give you RGB. See? So now if you can play with the color. Now if you want to red G, if you want to add some green, what will happen? Green plus red. You can do the color exercise. Yellow. Green plus blue. Or red plus blue. What will you get? Red plus blue. Pink. 0. All three colors. Okay. 255. 255. What will you get? White. You get white here. Yeah, see? Okay. So now you can get in beautiful colors. You can get pink, RGB. Yes. I hope this thing is clear for you. So by the way, if there's a representative in the group, please create a WhatsApp group and add me also so that I can quickly send messages. If you have a problem, you can ask uh, so that we have a communication channel. I hope this one is clear. Any questions? Yeah, I'm very happy that you are asking questions so that we can clarify these doubts. Maybe I'm not explaining them properly. Okay, it's very simple. Image generation. But now this is not what you want, I know. What you want to do is to open an image and do something with this, right? So displaying using my, so we open an image and display, but I want to be able to load that from uh, Google Drive, your Google Drive. displaying. Okay. So first of all, I'll show you my Google Drive and where I have kept the images. So this is my Google Drive. I have an images. There's an images folder. There are so many images in that. Beautiful images are there. I spent a lot of time in collecting these images. I have beautiful image. Let's open Natasha's image and display that. Okay. So now I want to use AI to open the Google Drive. It's not my thing, no. Uh, so the Google Drive. That I want to do. I don't want to do. I'm going to get it to complete that code for me. Yeah, see, this one I don't want to do. This one I don't want to do because this is not my thing. From Google.colab import drive, uh, then that's okay. Okay, so next time now I'm going to type my code. Import. You don't have to import again, okay? If you have imported these things in this so-called notebook once, that you don't have to import again, but I'm importing just for the sake of completeness. CV2 as CV. And also I want you to memorize these things. Import numpy as np, import matplot plot as plt. Okay. Im image equals cv dot imread, cv dot imread. So from the drive, I have to import the thing. So now here you will be able to see the drive folder. Uh, this is the drive. No, I didn't run this. No, that's the problem. I had run that. When I run that, you have to say connect to Google Drive. Please watch. You have to say connect to Google Drive. I have to give permission. And this is my account. That's fine. Don't send me email to this email address. I don't want to look at them. I use only the university one. So you have to give permission for it to access. Now I given permission. So it will mount the thing. Okay, it's mounted content drive. It's mounted at content drive. How do I access that? See this one. I don't know. Content. Yeah, there you go. Content drive. That's where the drive is. Okay, my drive. My drive. See, these are my folders. Now I have access to them. My drive. Where's my images folder? Oh, not there. Oh, I had a folder called images. My drive images. Yeah, there you go. Let's check again. Hmm. Images folder is not there. My drive. Due to some reason, the images folder I cannot see. Maybe reloading again will work. It was there. Okay. Anyways, so let's try to access that. Imread, uh, contents drive, mm, my drive, images. You want to access the image of Natasha.jpg. Okay. So now we want to whether we want to open that as yeah, just open it, and then we want to display that. So there's a little trick that you have to do before you display. Okay, let's see whether it's displaying. It's running. So figure, yeah, is fine. Hmm. If you do this, the colors will be horrible. Hmm. Maybe it's not opening that. Yeah, image has not been found. My drive images, Natasha from GPT. So maybe let's try this. Yeah, that's okay. But you see, the Natasha's colors have been totally changed. That's why we have to change the colors here. CV dot CVT color CV dot color BGR to RGB. I will explain the reason later. Now, if you run this one, you will see the colors will be correctly displayed. See, correct, correct. So this line of code converts the colors from BGR, this is the OpenCV format, to RGB, matplotlib. So because we are displaying using matplotlib, but we are opening the image using OpenCV. That's the reason. Okay, I hope this is clear. So this mounting the drive part is so important. What did I did? I already had that right. Okay. I hope it's okay. This images folder I still cannot see here. My drive. I was able to get it working due to some reason. Anyways, that's okay. If you have the image in the hard disk, the code here, the path will be different. But since I'm opening from Google Drive, I had to give the path in the Google Drive. And first of all, I had to give permission to the drive to access that for my this little piece of code, this mm, Jupyter notebook to access the Google Drive. Excuse me. Now, next one is displaying using OpenCV. That I cannot do with Google Colab. I had to do it on my VS Code. I have configured how I downloaded and installed OpenCV. I will show that also. From this folder list, you can see how long I have been at this university. Yeah, my folders from 2008. So I hope you know that how to use this. If you don't know, uh, let me know. I will create a video or something. This and see. Run, yeah, it's running. So I don't have an image folder in the your. I have a code in this folder. I have a folder called code. I don't have an image folder there, so I'm going to create an image folder. Just so I'll put an image there. I will put the image of mm, image of Mr. Tom Cruise. When an actor becomes very senior, you call him Mr. Just don't call him Tom Cruise, Mr. Tom Cruise. I don't need nothing now. Images, it's in the images folder. Tom dot jpg. That's fine. If image asset. This asset thing is very important to see the images and not none or something. This one, the messages, but I just want to. Okay. Then cv dot named window. So you have to create a window, something called a window. If you want to show it using OpenCV, then in that window, cv.im wait key 0 and destroy all windows. This is what it is. So you can see my Copilot is giving me the code. So when you run that, you will open the image of Mr. Tom Cruise and display. But this is a problem with the window. Yeah, picture of Mr. Tom Cruise. I hope you can see this. So this is the part of the course code. If you want to open that using, I will put that in the Google Colab file so that I can share that file with you. But it will not work in the Colab. So location of the image. What is the location of the image? Code is location. The image is in the subfolder called image, in the folder where this code file is. So to the code, this code file, we call it a notebook. I hope it is clear. This will not run in Colab. Yeah. So you can see in this code folder, I have the Jupyter notebook. I saved it, this one. And inside the image folder, I have the image of Mr. Tom Cruise. What an actor, right? Mr. Tom Cruise. He does his own stunts, apparently. Okay. Up to now, any questions or comments? How do we call this person Natasha? Her actual name is what? Natasha Romanoff is the name, the Black Widow name in the Marvel series. Her actual name is I don't remember. Okay, Scarlett Johansson. Thank you very much. Her actual name is Scarlett Johansson. See, you're helpful. Thank you very much. Okay, then we can display the image properties. You see, after we open an image, whatever, and show, we can show the image shape.im.shape, im.dtype, and im.size. So let's do that also. Yeah. My contact number is being asked here. Of course, it's public knowledge. This is my phone number. Please don't call me. If you please call me if I don't respond to WhatsApp messages or emails, then call me. That means you can understand, right? I cannot handle many calls. Yeah, call me if you're in emergency. So if you do not do your assignment, someone is going to have a heart attack. Then call me. Otherwise, WhatsApp message will be good enough. Okay, let's just get this image properties displayed. So let's open an image and display the image properties. Yeah, but now I want to open some other image. Um, let's open the image of beautiful Emma Watson. Import CV to as CV. That's enough, actually. Im equals CV dot. Oh, yeah. So this one I hit the tab key. Instead of Natasha, I want to open the image of a beautiful Emma Watson. See, it's giving me, yeah, um, image shape. image, data type, data type, size. Okay, let's display this also, right? Why just display this using this code? Yep. Okay, we have Emma Watson's picture. Shape is 810 by 720. You can see it's about 0, starting with 0, about 810. That's reasonable. 720, 0 to 720. You can see it's the size of the image. And 3 means it's a color image. Data type you int 8. Image size is this much. If you multiply this, and this, you will get the number. I hope it's clear for you. Maybe let's display this before this. Okay. Okay. Okay, those things are okay, I think. So all the codes work. Mhm. Then let's see how to increase the brightness, increasing the brightness. So I think open CV to CV, NumPy, SNP, all these things are okay. Now I have opened this image as grayscale image. You can see that I have written given a special command cv.imread grayscale to open the beautiful image of beautiful Emma Watson as a grayscale image. Then what I do is a CV add 100. I want to add 100 to that. Yeah. Then I want to get rid of the access. That's why this code is there. All other things are the codes that we already know. Okay, so let's do that. Increasing the brightness. Mhm. Other things I don't need. I think I need matplotlib. Image equals cv.imread. Content run drive Emma, and I want to open it as a grayscale image. Grayscale image. Of course, we assert bright image. Let's call it. Okay, shall we call it im1, im2, cv.add. We take im1 and add 100 to them. You see where the brightness increases. And display both these things together. So now I have two subplots, 1, comma 2. Yeah. Then I have to access AX0, and I show the first image. CMap gray. So you know that we need vmin and vmax also. Otherwise the display will not be correct. Huh? All right. Mm. Then let's set the titles also AX0. dot set title original image. Set title image with increase brightness. Yeah, fine. Then I wants to for I we have done by in okay, sorry, a in ax. I want to a dot axis on. I don't need no access now. All right, let's see how to increase the brightnesses. Oh, original image must be in one. What happened? What happened? Oh, this is 254. You can see the color has been increased. Brightness has been increased, not the color. I'm sorry. See, brightness has been increased, properly increased. But I will give you one more method of increasing, manually increasing. So I will say 3, in 3 equals in 1 plus 100, just at 100. And display that as the third axis. Incorrectly increase brightness, image 3. Oh, this is okay. Now you can see there's a mistake here, right? There's a mistake. I will not answer why that mistake has happened. It's for you to think about at home. So what we did today was we introduced what image processing is, what computer vision is, some advancements of that. And we briefly studied how to open and display images, how to create an image. This little piece of code also I will upload onto the Moodle. And so we can do a lot of work next time by doing image interpolation, this, that, and so on. Okay. So if you have a question, you can ask. Otherwise, we are done. You can log off. Thank you very much. Have a pleasant weekend, rest of the day. Thank you, everyone. Thank you.
Thank you.